So before we continue, I wanted to show you a new slide or new graphics which I just found about Gaia data for the differential rotation of our Milky Way galaxy. So we see here again the velocity as a function of the distance from the center of the galaxy. Down here are the different contributions. And then two different ways to describe it, with classical and fully relativistic description. And then, well, what we see that the models where we have data, they nicely agree. So the data is not able at the moment to say whether very likely the channel or the fully relativistic description should do it or should do the job, unless the classical description with dark matter. But I'm pretty sure that the relativistic description also includes dark matter. So we have the same in our galaxy, and do remember, usually it should have dropped this, basically this 1/r, or not here in here. But at some point with this 1/r squared, that doesn't seem really to be the case. Okay, the elliptical galaxies we have seen, and very likely that they were formed in the merging of galaxies, where we have all these nice pictures. So given you have 210 billion samples, then somewhere, if you look around, you somewhere will certainly find some of these samples are just in the process of merging. Okay, but we see also that the majority of galaxies is still have some spiral structure, either barrel spirals or general spirals. So then these irregularities, well, we clearly see where it comes from. So obviously there is some mechanism that makes our galaxies to adopt this. Well, if we have a disk, what is our first, that we have this flat structure. Well, of course, angular momentum conservation. Even if the original massive, supermassive gas cloud was spherical, in the moment it slightly rotates, it will split up into, or it will form a disk-like structure. Again, because the stuff that is in there perpendicular to the angular momentum, to the rotational axis, has more problems to fall in, while the stuff above or below can nicely dive into or go into the disk itself. Similar than the formation of the planet system that we had. But now we could take our different observatories and take a look at the spiral galaxies and where these spiral arms come from. I will later present a few slides, but first let's have a look how they really look like. So if we take this here, this is the so-called Whirlpool Galaxy. If we look at the optical, which is in the center, then we see solar stars similar to our sun, mostly. But there we already see basically this structure, the core or the bulk in the center, these two spiral arms going on. Beautiful. So for my sense of perception, this is quite beautiful to look at. Then, of course, we can look in the infrared. In the infrared, what we will see mostly. Indeed, you're right. Mostly we will see red stars. They are coming better out in the infrared because the Planck spectrum is now sitting more on this side. So what we see again, the spiral arms nicely reproduced with basically cooler red stars. they should make up most of the galaxy, because once created, they are there for a long, long, long time. And even in between, we see this basically these filaments going there. This is now very interesting that we have here. This looks a bit almost like a connective ways between the spiral arms. We can, of course, look at the radio. In the radio, we will mostly see hydrogen gas with this 21 centimeter lines, or if it's cool enough, we can also look for other gases like carbon dioxide, like it's done here. But this, again, we see that a lot of this gas seems to be mostly in the spiral arms. So we can assume that also if we would look for the hydrogen, it would look relatively similar. And therefore, we can assume that star creation is going mostly in there. Going towards the harder or the harder light, so ultraviolet X-rays. This is then going from the optical. We jump to the right. What stars are more in the UV? Well, there's the very young ones. And so you remember before the outer layers have settled, we can look deeper into, we see hotter regions, therefore the Planck spectrum is shifted more to the UV. But also, of course, the big ones. Remember the very short-lived rock stars, they are very hot on the surface because they produce so much energy, they burn so quickly off their fuel, that their Planck spectrum is also mostly in the UV light. This should give us, because they live so short, a couple of 20 million years, this is for a star nothing to migrate long around. These stars are very close to the regions where they are produced. So blue stars are basically the markers also of star creation. Oh, clearly we see there's loads of going on in the center. And the spiral arms seem to have occasionally region where more is going on, but not so much, not really continuously. What is a bit surprising for me. I would have expected for what is later to come that there is some kind of along the spiral arms more consistently. The next thing is we can, of course, look for extreme objects, which then would accelerate any gas nearby extremely, therefore create the plasma. The plasma will create, again, jets or very high energetic radiation, or comparably high energetic radiation like X-rays. So some source of big mass that can accelerate fast. That should be, if you look with Chandra or XMM Newton, or as Callum did nicely in his work, Astron, a Soviet satellite, which was one of the first X-ray satellite. We see that, of course, there's much going on in the center, and I wonder a bit out here, and occasionally, again, if we overlay this at the spiral arms. So obviously, these points are relatively identical. And then individual points, which I would assume there are neutron stars. Whirlpool Galaxy is not that far away, but we can also look closer. Do the same game at our neighbor Andromeda. Visible again, this nice spiral structure of Andromeda, but it seems here a bit more ring-like. Then we look at the infrared, we see the older, cooler stars. The red ones, the smaller ones. Radio, so atomic, we see that the atomic and molecular gas distribution, and we see this not so much in the bulk, what I wonder a bit about, but rather in this region around. and then a bit more outside, and then UV, again, the big blue stars, the hot younger stars. Again, in the center a bit, but this might be also different. That comes from the X-ray source. So again, in this rings that we also see here, rather the reddish ones. But then in the center, we have, of course, a big source of X-rays. So, not to make a big fuss, there very likely we have a supermassive black hole. Supermassive black hole means every gas that is nearby will start spiraling around, and the acceleration towards the black hole is relatively strong, what means we get a fast-moving, very likely fast-moving charged particles or charged plasma, and therefore lots of radiation. Another example would here be this M104, which is also called the Sombrero Mexican Head Galaxy. So big ring. And then we see here nicely a bunch, and we see these globular clusters around. So to make a picture, one sees here then 3 spiral arms. We see a bit of a halo, obviously, around. Interesting, this halo is mostly gas, but also occasionally the one or other odd single star. Then we have these globular clusters, what means this accumulation of a couple of 100,000 stars, like a liquid drop, bound by mutual gravity, so forming some kind of small satellite galaxy. Our disk, and in there the spiral arms and what is then often called the nucleus, or the bulk in the center. So again, looking with Chandra, we see a bit the halo, but mostly the center. Optical, well, yeah, I wonder if it's really that green or whether this has been later colored. And then with Spitzer, we see the infrared there, we see nicely, basically, really the disk-like shape of this galaxy. And I guess this here is then all together. So, okay, the disk is basically, again, we have 1 or 2 gas clouds or merging, and there's some rotation included. Then immediately we get basically the angular momentum, we get this barrier for the stuff that is in this plane. That is perpendicular. If here the rotational axis is going north-south, then everything in the equator plane has problems to fall in. Of course, also the stuff that is up here, but the stuff up here has now also the chance to migrate down into the disk. Or then with time, we have then created the disk. Where the central bulk appears or comes from, we usually often find here in the center some spherical bulk or some barred spiral. It's not seemingly not completely understood, but ideas go towards cosmic or galactical cannibalism. So far as this module now come to, that we have basically cannibalism amongst galaxies. Dwarfs, corpses of stars, cannibalism of galaxies. Oh my God, this is a horror module. So basically, and with the arms, well, I'm soon going to present basically some ideas. It's a bit of an enigma because if galaxies formed about 30 billion years ago, and now the stars that are formed might have then all a bit different velocities. You remember when they were formed in the same region, then there might have been a bigger one which whirls the smaller ones around, and they might get all a bit of a different velocity distribution. So why is the structure in the 13 billion years not disintegrated? Oh. So this is a bit of an enigma. It can be, of course, that this common center of gravity causes some kind of reorganization. So, well, now how can we basically make of this individual chaos a big global structure? So local is chaos, but on the big scale, we want it all organized. In order that these arms could form, there is one theory is basically you have ellipses that rotate, and then you need occasionally to hold the stuff that is coming from the back. This is some kind of traffic wave or traffic jam density wave model. So on the motorway, when you drive, there's no particular obstacle usually. Most people will drive with a relatively similar velocity, and you can nicely drive along. But then there's, of course, at some point a slower vehicle coming, and there it starts to congest. It just needs one of the guys that is a bit slower, and then you congest behind. And you have these nutters that need to come very close to the guy. He's a bit paranoid and he slows even more down. And well, or if the truck is big and you have to drive, and it's relatively narrow, even if it's 2 lanes, then you automatically slow down. Also, if you drive into a tunnel, most people then slow down. So behind the tunnel, at the entrance of a tunnel, there is usually also congestion. So what would be now here the truck? What would be the car? And this would be basically that the trucks would be the dust and hydrogen gas, so making a viscous medium. And the cars are the stars. So if the stars come into this viscous medium, there might be a bit slowed down. Then, of course, the others come with full speed and get the congestion. This would be one thing. Another thing is this is now really, well, nice animation. I won't click on this video. I would recommend you to stop and then basically on the lecture slides, click on and enjoy this video. What you see is basically stars going in concentric circle at the beginning. Then somehow this circle, this symmetry is distorted. For example, there's on the right-hand side another big mass that then attracts the right side more than the left side. We get ellipses. And then this big mass wanders a bit around. This means we get now a bit of a twist in. And then you will see how we get this from the original circular rotation. We get the nice pattern that reflects basically these spiral structures. Just make a bit of an ellipse and let's start having this ellipse or the stuff on the ellipse going still around. But then if you look here, what will we see? We get this filament structure. This was here nicely to be seen. That we have basically here some kind of almost connecting fibers between the two spiral arms. So I would say enjoy this film. and after this film, I can tell you everything I want, because you're probably hypnotized. But it's quite nice how to make such structures, regular structures. Of course, you have at the beginning, we have a highly symmetric system, and we slightly break the symmetry by making ellipse. From the spherical symmetry, we go to the elliptical one. It's a lower symmetry. And then we distort it slightly, twist it, and immediately we have this stuff. So this means there are models that can explain this. Enjoy this video, and then hopefully you tune in back to this video. And then we go on. So you have seen now basically this mechanism, hopefully, to create the stuff. And then what we usually have also observed was that the older stars, they can be better distributed, also in between the spiral arms, like our sun, 5 billion years. So wherever it has been created in the Milky Way, it's not reproducible anymore. We wouldn't get back. Therefore, the system is too chaotic. What means small changes change the big evolution of the system. We can't trace back everything. So we won't know the sibling of our sons, of our sun. As you remember, they are always born together. So then usually we've seen that the gas is all concentrated, at least in big fractions here along there. Spiral arms, and of course in the bulk, and a bit below and above, but not too much. So here this galaxy seems to rotate clockwise. So, and then we find the younger stars in the spiral arms. That is clearly explainable. If the gas is concentrated in the spiral arms, this is the birthplace. And then if we have there a region of gas that is faster hitting a region of gas that is slower, then of course we start creating these instabilities that we need, that the gas cloud starts to collapse, contract and collapse. So that would be the general outline of a spiral galaxy. And you have seen how we could create this pattern, whether it really the way it is. But then we have now nicely this galaxy or these structures. But why do they often have a bulk? Why do they have occasionally even this part structure that here is basically almost like a linear bar before the spiral arms start. It might be also that galaxies are often clustered together. You remember the superclusters. And if they are in clusters, this means occasionally they are so close, despite that the space expands, they are still so close that the gravity is stronger than this expansion of space, and then they attract each other. If it's some equal masses, like Milky Way and Andromeda are roughly the same. I think Andromeda is a bit heavier. There's then also one hears that suddenly the mass of Andromeda is just half as assumed. And for me, as semi-layman, it's a bit hard to filter this out in astronomy. So if they are equal partners, I would talk of a merging. But what you're going to see is that there are, of course, at the galaxies that are born in a more dense region, they are more mass rich, more dense of original gas. They are more mass rich, and others that are born in less dense region. Remember the cosmic microwave background? Notice original density seeds. And what happens, of course, if such a smaller if they trap each other in the usual gravity? But of course, we would assume that the big one is eating the small one. So it comes to cosmic cannibalism. A beautiful, almost beautiful. Oh, good, it's so it's almost something to meditate about. Is the simulation here that shows basically the early universe and how galaxies basically cannibalized. So even how spiral galaxies merge, become elliptical, then elliptical merge. And when elliptical merge, there might be again a mechanism where angular momentum is involved. If they do not hit centric, if they hit a bit on the side, then you have angular momentum involved. Then you get some kind of flotation. But then you form again a disk-like structure. Strange stuff. So I would recommend you again stop this video, enjoy this here, this kind of stuff. And then it's of course interesting for you because now we talk again about very recent finding published to us in 2020 or 2021 about our Milky Way. 90% of the stars rotate in one direction, 10% in the other. The only explanation is these 10% come from other galaxies that our Milky Way has eaten. Our Milky Way is a cannibal. Oh, well, Easter is coming soon, the lambs are born, and our Milky Way silenced them. So here is basically the from finding from ESA shown. But then you see in this, there's at the bottom a film showing basically how the Milky Way eats a smaller galaxy. And then you see that we have there some bar-like stuff resulting in near the bulk or near the center. Of course, whereas most of the stuff will end up, of course, in the center, in the bulk. So the bulk might be just a sign that the bigger galaxy had just a good meal. And the same is true for the bars, that they are responsible for this, the feasting, the eating is responsible for this bar structure. So nicely again shown here. So this Gaia is fantastic. So this satellite was worth every penny. And with this, I would now stop because the next topic will be active galaxies, or radio galaxies and quasars. Whoa. That will be then for the next video, which will be a bit longer.